We have covered a lot of ground with respect to the TCP protocol. In this video, we will wrap it up. Before we proceed further, I would highly recommend that you refresh the sliding window concept as learnt at the link layer. So go through the slides and come back. So our journey with TCP started with the kind of services TCP provides. In this context, we also looked at the TCP header format. Then we moved on to connection management, where we looked at some interesting problems associated with establishing the connection as well as tearing down the connection. We then moved on to congestion control, which is a very complex problem, which TCP handles beautifully. There are issues, no doubt, which later versions rectified, but overall, given the complex task, TCP does a very good job. In this video, we will all put it together in the context of the sliding window protocol. In that context, we will also address this flow control problem and also cover some miscellaneous implementation aspects. Flow control is about managing TCP buffers. So that is the problem we are looking at right now. I mentioned earlier that TCP is a connection-oriented byte stream protocol. In that, the application process writes bytes into the TCP send buffer and the receiving application process read bytes out of the TCP receive buffer. This picture should be familiar with something you have seen as part of the sliding window protocol. There was the last acknowledgement received that translated here into the last byte ACK, and then there was the last frame sent, which translates in here to last byte sent. And there is something new here, which is the last byte written, which is here. So at the receiving side, we have next byte expected. There we had last frame received. Here we have next byte expected. That's because TCP doesn't acknowledge what it receives. In fact, it asks for what it wants next. And then there is the last acceptable frame, which there is nothing that translates to in here because things are done slightly differently now. So we have two other things new. One is the last byte read. So this application process is reading the bytes. So this read at this particular point, and the last byte received as far as the receiver is concerned. Naturally, these relations are true at the sending side in that the last byte ACK will be less than or equal to the last byte sent, which will be less than or equal to the last byte written. And similarly, at the receiving side, the last byte read will be less than the next byte expected, which can be less than or equal to the last byte received plus 1. Why is this 1 arising? In case there are no holes, next byte expected will be 1 more than what was received properly. When we covered the sliding window protocol, there was an underlying assumption that these buffers are infinite. It may not have been obvious to you, but that was the underlying assumption, and you are sliding the window across these buffers. But in reality, these buffers are not infinite. They have a finite size. In fact, I mentioned that during the TCP connection setup, you allocate some space for these buffers. So the amount of space you allocate for the sender side, we will call it max send buffer, and at the receiver side, we will call it max receive buffer. This thought must have occurred to you. How do these relate to SWS and RWS? Do you think they are the same? Nope. SWS is very different from the max send buffer. SWS is dictated by the bandwidth delay product of the network, whereas max send buffer is an implementation aspect where you have decided upfront that this is the amount of buffer you are going to allocate for this connection. Naturally, you do want this max send buffer to exceed the maximum bandwidth delay product possible as part of your connection. Otherwise, it is going to be inefficient, but SWS is what is going to drive the amount of data you can send. Max send buffer is just the storing place for this data. Similarly, RWS is not the same as max received buffer. If you set RWS is equal to 1, that means you want to achieve in order delivery without having to do anything more sophisticated. But for efficiency purposes, you would like RWS is equal to SWS. So this RWS is also dictated by the bandwidth delay product. Whereas this max received buffer is again an implementation artifact, and naturally again you want your max received buffer to also exceed this maximum bandwidth delay product. But in some cases, depending upon the implementation, it may not exceed because that particular device is resource constrained. So here are two relations that arise because we are limiting the buffer size. So here we need to ensure at the sender size that the last byte return minus the last byte act is always less than or equal to max send buffer. And similarly at the receiving side, you need to ensure that the last byte received minus the last byte read is always less than or equal to the maximum receive buffer. If you don't ensure these, you're going to overflow these buffers. Now let's focus on the receiver side. You tell me what cases can arise which can cause this receive buffer to overflow. There are actually two cases that can cause this. One, if you set your maximum received buffer less than the bandwidth delay product. This, as I said, can arise because the receiver is resource constrained. It's not efficient, but what can you do? You don't have enough resources. What if you set your maximum receive buffer to be greater than BDP? What can potentially still cause the receiver buffer to overflow? Well, if this application process here is not reading this data, then also your buffer is going to overflow. Flow control is about avoiding this overflowing of the receiver buffer, whereby the receiver controls the sender and ensures that the sender doesn't overflow its buffer. So how do you think this can be achieved? You know the answer to this. We have seen this as part of the TCP header. So the receiver could advertise to the sender the exact amount of free space it has. So this goes via the advertised window field as part of the TCP header. Can you express this advertised field as part of these parameters that you see at the receiver side? Advertised window basically captures the free space available at the receiver buffer. So here is the answer. If you didn't get this exact expression, don't worry, there are a few subtleties involved. So if you notice here, this portion you don't have to store in the buffer because the application process has already read that data. Suppose this is your maximum receive buffer size. Now this is being occupied by this portion, this portion, this portion. So you will tell the sender that this is the free space available at my end, which is the maximum received buffer minus this portion. Now you must be wondering what happened to these light blue portions, which are the out of order deliveries. You don't send this information because of the way the TCP sender acts based on cumulative acknowledgements. As far as the TCP sender is concerned, it doesn't know the status of this. So it is going to view these still as being in the pipe and will account for them when sending. In other words, the receiver doesn't have to tell about this. The sender will keep track of this. When we see the sender side, this should become obvious. So to summarize, this is what you are going to advertise: the overall space available minus the in order deliveries that you have received. The sender side is a little bit more complex. It not only has to avoid overflowing the receive buffer, but also it needs to ensure that it doesn't congest the network. So for this, it needs to ensure these two things. In other words, the last byte sent minus the last byte acknowledged should be less than or equal to this advertised window. And similarly, the last byte sent minus the last byte act should be less than or equal to CWND. So you ensure that both these conditions are met by defining a new variable called max window and taking the minimum of this. That is CWND and advertised window. And then you calculate what is called an effective window. Basically, that determines how much data you can send, and this effective window is given by this max window minus the last byte sent and the last byte act. So this is the amount of data you can potentially send. And you will only send data if this effective window is greater than 0. For now, let's ignore CWND and focus on the advertised window. In other words, let's assume that the advertised window is less than CWND, in which case what has been advertised is this portion. And now last byte sent could be more than this because there are still packets in the pipe, and last byte ACT could be less than this because the sender did not receive all the ACTs. So there are some ACTs also in the pipe. So from this advertised window, you're going to remove this portion, and whatever is remaining, if it is greater than 0, you can send data. Now, as you can see, these packets have been accounted as part of this calculation. Well, this is a bit of a worst case scenario. The best case scenario is where the last byte ACT corresponds to the next byte expected, and the last byte received corresponds to the last byte sent, in which case you're going to remove this portion and then send the remaining data as dictated by the space in the received buffer. Yeah, I know this is all a bit complicated, but go through it a few times, you will understand what's happening. So what we have seen so far is the sender side not overwhelming the receiving buffer. How do you ensure that the send buffer doesn't overflow? So to achieve that, what is the relation that you need to maintain across these variables? So you do need to ensure that the difference between the last byte written and the last byte ACT is less than or equal to the maximum send buffer. In case this buffer becomes full, you're going to block the sending process and not allow it to write. In other words, when you do the socket programming and when you call send and are passing some message as part of it, this function will not return until there is space as part of the maximum send buffer. So this is how flow control works. So let's talk about the case where you set your maximum received buffer to be greater than the bandwidth delay product, and we'll talk about the case where the receiver process is very slow. So how does it then stop the sender from sending data? So what happens in this case is first the receiver buffer fills up because this last byte read is not incrementing since the application process is not reading the data. Then slowly the sender, since it keeps sending, this received buffer is going to fill up, and at some point you fill it up, in which case you advertised a window of 0, and then the sender, because you're advertising a window of 0, cannot send any more data, and thereby the sender buffer starts filling up, and finally you're going to block the sender from writing any more data. There is one last point we need to handle, in that how does the sender know when the advertised window is not 0 so that it can send additional data? The immediate thought that occurs there is the receiver can tell the sender whenever some buffer space frees up in the received buffer. Unfortunately, the design paradigm of TCP is the smart sender dumb receiver, in that the receiver does not spontaneously send ACKs. It only acts when it receives packets. So this process simplifies the receiver design. So that is why it acts in that particular fashion. So if that were the case, what can you do? The sender now has to assume the responsibility of determining when the advertised window exceeds 0. So what the sender does is it periodically sends a 1 byte segments. Very likely this will not be accepted by the receiver. It can get dropped. As a consequence of this, the receiver is going to send a cumulative acknowledgement, well, not acknowledging this byte, but acknowledging the previous byte. And as part of this acknowledgement, it will also tell what the advertised window is. So at some point, the receiver will advertise a non-zero window based on which the sender can send more data. So that's with flow control. Up ahead, we will look at a few implementation issues. A good time to break.